Welcome to Picture Language Seminar. It's October 3rd in Cambridge, Massachusetts, and we're continuing our experiment to do our seminar in hybrid mode. It's really tremendous to have Madhu Sudan speaking to us today. He's professor of computer science at Harvard, and he's going to talk about proofs and computation. I'm looking forward very much to your talk, Madhu.
Thanks, Arthur. Thanks for inviting me to this forum. It sounds wonderful. And I do look forward to seeing some more videos from the forum from before. Today, I'll talk about proofs in computation. Let me get the screen share up, and then I can focus fully on the talk. There we go. Okay, great. So, I don't know how many of you would look at this title and be able to predict where the talk is going to go. Let me start by saying it's not going in the direction of computer-assisted proofs. I mean, there are all these wonderful proofs that have been found in the literature in the past. The four-color theorem, Kepler's, the Kepler conjecture and its resolution by Hales. And there's even an entire book by Wilf, Zeilberger, and Petrovsky called A equals to B, and how this book basically just tells us how you can find proofs of lots of very interesting equalities in math by running computer proofs, computer searches. That's not what we're going to be talking about. Instead, what we're going to talk about is some sort of a triangle, a collection of relationships between mathematics, proofs, and computing. And I want to set up the stage for where we go. So here's the very quick overview of the talk. So anything from time minus infinity to 1950, I consider prehistory. This is just, before we even understood really completely what a proof was, I think. The ancient history to me is anything from the period 1950 to roughly 1980. Recent history is something along the lines of 80 to 2010. And then I'll also talk about ongoing themes, which are maybe even relating physics to math and computing and proofs. So, and maybe even the future. So I don't know how much of these slides I'll get through, but if people have questions at any time, please feel free. I'm more than happy to, engage with you. And if it means that we'll have to sacrifice a few slides from the end, then so be it. All right, prehistory, this is the era where we're trying to understand what are provable statements. So, of course, formal logic, this is an arrow from mathematics to proofs, which says, we want to, proofs are the language of mathematics. You want to prove anything, then, we want, the only statements that I would consider mathematical are those that are associated with a proof. And this originated independently in many different civilizations. I won't get into the details of it, but the time when we started realizing there is also mathematics that can be applied to studying proofs. So proofs were how you express mathematics, but now we're suddenly saying, oh, mathematics is how you would study proof. This started from the work of George Boole in 1850, during this period. And there was this very strange math when everybody else was trying to extend the scope of their numbers from integers to rationals to reals, complexes, quaternions, or whatever, Boole went down all the way to the basics and say, oh, let's look at the mathematics of 0 and 1, along with the operators and or not, and suddenly, all kinds of interesting things flowered. I don't know if you've ever taken a look at this book by Boole. It's got a very grand title, it's about logic, probability, philosophy, all of this appears in the sort of this byline of the title, and neuroscience is all packed into this title. Then that's just the title of the book. But anyway, he has this very interesting thing. So you can use math, apply math to do some logic. So for example, if you believe that repetition of a sentence does not add to the knowledge, then as a principle, you should get as a consequence, you get the principle of contradiction, saying, at the same time, a statement and its negation cannot both be true. And he does this by, somehow doing a sequence of steps, like, here's the kind of logic that you see in that book. Okay, so it's very interesting. So now we started talking about how mathematics can capture proofs. And this has roughly led to a lot of very rich sequence of rich interactions, very remarkable period. In particular, Cantor's work, which really sort of started setting up the foundations of and started challenging this thing that, oh, we could capture everything completely purely logically. Hilbert's work, Hilbert more or less was convinced that, oh, mathematics will be capturing everything. There is no statement that cannot be proved. That was probably the ongoing thought behind many of his works. But then Gödel came along and said, oh, look, but there is this notion of incompleteness. And it's sort of roughly, it corresponds to the statement, paradoxes like this statement is not true, but that statement actually could be true, could be false. This is not the statement that's actually the real incompleteness statement. The statement that's actually contradictory is this statement is not provable. Because now if you can prove it, then obviously that statement is false. And if you can't prove it, then the statement is true, etc. So, but then you can't prove it. So not everything is provable was Gödel's work. And then Church and Turing sort of extended Gödel's work and put it in a very, very, very clean framework. Gödel sort of worked with the eccentricities of number theory, which was not the right language for logic. Turing's work in particular, who invented the Turing machine so that we could actually talk about logic. I mean, that was the whole reason. Nowadays, it is the model for what a computer is, the idealized model of a computer, and really a pretty good idealized model, I would say. I mean, it's not like outrageous to start comparing your laptop out here to a Turing machine. So Turing's machine, of course, is a sort of a central ingredient in theory of computing. So there is this notion of a computer. This is always sitting around. And this is a model of a computer in which you have some finite state, which is controlled. And you can do whatever you want with a finite number of states. So it gives us a very, we are not being very particular about what a machine can or cannot do in a single step. We are giving you complete freedom, but it has to be a finite amount of control. You cannot build an arbitrary amount of control. And then you have this infinite tape in which you can store information, write information, read from it, and move along from place to place. Everything is done using a sequence of steps that's completely determined by the finite state control. So nothing is left to a non-determinism. So this remarkable construction, helped, both solidify the theory of logic and the theory of computing. And it pretty much had a direct impact, I think, on the von Neumann architecture, which is much more closer to the existing computers today. So the story, why did Turing talk about this? Because he said, look, proofs are objects which have to be mechanically verifiable. Okay, but how do you define mechanically verifiable? He said, well, mechanically verifiable is anything that can be verified by a Turing machine, by his machine, which we now call a Turing machine. So if you wanted to say something is an automated process, but the automated process seems to involve, you want to give this automated process full flexibility to capture whatever you think is natural. But at the same time, it should not be so rich that it just sort of looks visually at a proof holistically and says, yes, this is correct. It has to be something that goes mechanically through the proof and verifies it. You want to define that mechanically verification, you want to define any mechanical automated sequence of steps, you need something like a Turing machine. And that's where he invented this. Okay. So theorem is any statement that has a proof. Incompleteness says that there are theorems for which there is no, which are completely consistent with the system of logic, which would not admit a proof. So this is how you express the inability of logic at the time. But almost all of this initial excitement about logic, or maybe sort of disappointment with logic, almost always actually, they didn't really understand the difference between a theorem and its proof. So let me illustrate this. So ideally, what do we think a theorem should look like? It should be, you start with stating the theorem, saying this is the statement that I want to be true. Today, you will write it as a sequence of bits. And then you start writing a proof where every line of the proof either comes from the axioms or immediately follows from the previously derived statements. Okay. So you would write some statement pi1, then pi2, and then pi3, each one of which is clearly logically following from whatever you've established so far. At the end, you should come up with a statement which says T. Of course, this is mechanically verifiable. There's no doubt about this. The problem with this definition is here is another proof which is also mechanically verifiable. I just say, look, here is the theorem T, the proof. I just say it has L lines. Okay. And why do you find the L lines? Well, go ahead, search for it. That's only a finite search. Finite searches are mechanical. So go ahead, do the brute force search. Okay. So there's a difference. We would not accept the latter as a proof. The former is a proof. The left-hand side is a proof. The right-hand side is not. But this has not been captured in the entire history up until 1950s, which is why I was calling it prehistory in a sense.
This is what some students do on a test.
Well, yeah, okay, there's also, I mean, okay, we'll talk about some students and their proofs also later in the thing. Maybe a little bit more clever than typical students' proofs, but we'll see those things. Okay, so yes, indeed. So you cannot accept the latter. And the reason we should not be accepting the latter is that the former actually takes L steps of verification. You know, it's a proof of length L, but also each step can be verified in roughly constant amount of time or maybe linear time. So some polynomial amount of time would have sufficed to verify the proof on the left. The right-hand side proof, I would have to enumerate all the possible statements of length L, and then find out which one of these is true. The second part is mechanical, but the first part is like a brute force search, and brute force search should be excluded. The only way to exclude it is to quantify computation. So you now have to develop a notion that some computation is easy and fast and really mechanical, and some is slow. And that is the essence that was missed out so far. So we now turn to this question of what is efficient verification. Okay, up until now, we know what it is to be mechanical, but we don't know what it is to be efficient. So let's talk about efficient. So this is the origins of modern complexity. In a letter from Godel to von Neumann, he actually asked basically this question: is there a more effective procedure to find proof of length L if one exists? So, you know, can you find one in, say, L square steps or L cubed plus 10 times L squared, whatever? I mean, any of these would be considered much more reasonable than something which says, if there is a proof of length L, I will enumerate all the possible L-bit strings and find out which one of these works. Okay. So Godel really posed this question in these letters to von Neumann. I don't know that it actually registered on the other end, but definitely the questions were asked. And this is really the beginnings of what we would now call the P versus NP question. Cobham, Edmonds, Hartmanis, and Stearns, all of them started looking at this thing. You know, one thing is, how do you quantify the number of steps of computation? This is not an easy notion. Turing, by his very clever idea of building a finite state control, said we have complete flexibility on what our Turing machine can do, what our computer can do. But in doing so, he created a very weird calculus in which 10 L squared steps of computation cannot be distinguished from 5 times L squared bits of computation. So any constant factor speedup is possible. You give me an algorithm for something. If I build a computer which is maybe twice as big, I can make it work half as many steps. And this is somehow essential and inherent. This is not an artifact that we can try to walk around. So this looked like a real serious challenge. How do you deal with computation when I equals I plus 1, the integers don't make sense? But there is something very interesting about these asymptotics and the way you can set it up. You can set up a clear notion of, you know, complexity being larger, as long as the difference in the functions is not just a constant factor. Okay. So L squared is actually a very different function than L to the 1.9. And 2 to the L is definitely very different from 1.9 to the L. and definitely very, very different from L squared, etc. So you can differentiate exponential time from polynomial time. These are formally different. There are problems that can be solved in 2 to the L time, which cannot be solved in L square time by any computer. But there's no problem which can be solved in 10 L square time, which cannot be solved in 5 L squared time. In fact, every problem has this kind of a speed up associated. But because we have this coarse separation, we can define the notion of problem solvable in polynomial time. It is a crisp notion. It is not loosely defined. It is not subject to your model of computation. It is not a function of the exact Turing machine that you're building. All Turing machines, universal ones, will be able to run all problems in polynomial time. In some polynomial time, some may be slower, some may be faster, but it will be polynomial. So this allowed us to talk about P, the class of all efficient computations. This is, from now on, things that are efficient. Going back a page, we should be thinking of when we say a proof should be verifiable nicely, well, it should be verifiable in polynomial time. So this is the formal language which sets up the notion of a proof. So Edmonds, brilliant mathematician, largely self-taught, sort of, I think he didn't even have a PhD, and so just has a master's or something. He conjectured the following, that the traveling salesperson problem is not solvable in polynomial time in this class P. Okay, he was the first person to make this concrete conjecture. Maybe in 1965 or so, he wrote this in a paper, and then others followed up on it. And there's some very interesting quotes associated with it, but I'll sort of skip it. But it took a little while, another 5 years, before Cook in the US, he was in Berkeley then. Actually, Cook came up with this brilliant theorem. This is the beginnings of the theory of NP-completeness. He was in the math department at Berkeley and didn't get tenure there. So, and then had to move over to Toronto, where, of course, he eventually got the highest award in computing. So it's a story about how computing was viewed in those days, maybe. Levin was in Russia, student of Kolmogorov, and the two of them independently sort of started to build this theory of NP-completeness. What does this theory really talk about? It really talks about, what is the complexity of proving a theorem. So I give you a theorem statement, and then I give you a length L, saying, I think there's a proof of length L. How long will it take you to find that proof? So find me a proof. This problem, we believe, should be as hard as any of the brute force search problems out there. And that's what really got Cook started on this problem. He really examined this question and said, yeah, there is an entire class sitting around it, and I can work other things into this thing. So they formalized Edmonds' conjecture. NP is the set of problems where you have efficiently verifiable solutions. For us, the most canonical NP problem is I give you a theorem and a proof, and I ask you the question, does it have a proof of length L? That is an efficiently if you have the proof, it's easy for me to check that it's of length L, and I can verify it step by step. That's our definition of being a proof. So NP problems are any such problem that looks like this, where I can prove to you that a solution exists, but finding that solution may actually be hard. And NP-complete problems are those amongst these problems in NP which seem to be as hard, which are as hard as any other, which are provably as hard as any of the other problems. If any of these NP-complete problems end up having a polynomial time solution, every problem in NP, any problem that can be simply, you just have to, in order to, the former way of specifying a problem is I just tell you how I will verify a solution. That's it. And that is good enough to find the solution if NP equals P. So, and Cook's theorem in particular said the theorem-proving is an NP-complete problem. That is why the title of the paper is The Complexity of Theorem-Proving. So there are many other problems that turn out to be NP-complete, something called satisfiability, if you know what it is, graph 3 coloring. I give you a graph with nodes and edges, and I want you to color all the vertices, so that with one of three colors, red, blue, or green, such that no edge is monochromatic, both endpoints have the same color, etc. Lots of questions. And Gödel's question really was asking, in the letter to von Neumann, he was really asking, is NP equal to P? Optimization turns out to be sort of somehow was really looking for this concept of NP-completeness. And Edmonds, who was sort of a person working extensively in combinatorial optimization, this is what he was really hoping for. And finally, Karp actually proved, just a host of, there are at least 19 problems which he showed to be NP-complete from different domains, and then basically made it pretty clear to anybody working anywhere close to this space that NP-completeness is something that they should care about. I mean, you work in number theory, there's a quadratic assignments problem. If you're working in algebra, there's some other problem. If you're working in logic, there's some problem. If you're working in graph theory, there's some problem, etc. Huge collection of problems that were shown to be NP-complete. It became clear this is something that's very important to us. So here are some NP-complete problems, like, can you color this a given map with 3 colors so that bordering states have different colors? Okay. You should assume that this point doesn't exist, because otherwise this may, sorry. I can ask this question about any graph, any map. In general, we when the 4 coloring thing is proved, that's usually assumes that there's no 4 regions which are sharing a point. So anyway, so you can ask this question, does it have 3 different colors? You can also ask the traveling salesman question, which is send a traveling salesperson on a route which will visit all these points. I think this is a TSP visiting the 13,000 most populated cities in the US and returning to the starting point. So you go to each one once, and then you come back to the origin. What's the shortest path? In all of these cases, when you state the question properly, is there a path which uses at most 17,000 miles? It's a well-defined question. If there is a solution, I can prove it to you. I'll give you the cities and the order in which you should visit it. It's only 13,000 lines long, this solution. You can go ahead, verify every city has been visited, and you can make sure the lengths are adding up to at most 17,000 or whatever our budget was. But on the other, find it, it's ridiculously hard. So that's the kind of problems that we are looking at over here. There are many places where NP-completeness has applications. And for proof checking, NP-completeness has another very nice consequence to it. It's a way, every NP-complete problem, you should really think of it as a format for verifying a proof. Okay. So 3 coloring is NP-complete. Yes, go ahead.
Can I ask you sort of a naive physics question?
Absolutely.
When you say, that these are the hardest problems in NP, that's a vague statement. Is this like irreversibility in physics, or what?
No, okay, this is a very formal statement. I didn't clarify it. Good. So there is an algorithm that I already have, which, so for every NP problem, any NP problem, take it. For that problem, because it's an NP, that's a form, there is a formal way in which you describe it. Starting from that formal way in which you'll describe it, I will be able to build an algorithm which will take any instance input to this problem that you want to solve, map it to an instance to an NP-complete problem. So let's say we're looking at 3 coloring is my NP-complete problem. Take any NP problem that you have. I can map the input to this problem into a graph. If this problem has a solution which the verifier would accept, then this graph will have a 3 coloring. If it does not, then it does not. So if you give me a polynomial time algorithm in particular to an NP-complete problem, then I can give you a polynomial time algorithm for every NP problem. Okay. So it's a very formal statement. It is the hardest in this loose qualitative sense, just because this problem is solvable in n square time on inputs of length n, does not mean every problem in NP will be solved in n square time. Some may take n to the 4, and some may take n to the 10, and for each constant there is a problem which will take at least that much time. But everything will be polynomial time solvable, whereas right now the best things that we have are exponential time. Yes.
the contrary is also true, right? If you have an NP hard problem, then you can reduce your problem to the existing NP hard problem to show that hence your problem with NP hard.
Right. So there is this. So reductions are transitive. So if I reduce a problem A to B and then B to C, then I can also reduce A to C. And as a result, this network really expands very nicely because of this. Karp gave this, 20 in order to prove that 19 problems are NP-complete. How do you prove in one of my courses that a problem is NP-complete? In principle, you should give me infinitely many reductions, one for every NP problem. But I'll say, oh, that's too much for us. I'll give you the idea of how Cook showed that satisfiability is NP-complete. From now on, you can assume satisfiability is NP-complete, but in order to prove three coloring is NP-complete, you reduce satisfiability to three coloring. Now, by transitivity, everything reduces to satisfiability, and satisfiability reduces to three coloring, and you're done. Okay, great. Thanks for this wonderful questions. Okay, so but by the way, this exact philosophy, this whole thing that I've been describing is almost exactly what I want to comment on again here. Remember, theorem proving is an NP. Graph coloring is NP-complete. What is theorem proving? An input to theorem proving. I give you a theorem, and then I give you L blank spaces. Okay, so that's the length, that's the input. I would say fill this part so that the verifier will go through this and conclude that yes, the theorem is true. Okay, this is a proof of that theorem. So that's an input to theorem proving. Graph coloring is NP-complete. What does that mean? It means that I can take this sequence of bits which represents this theorem and the spaces needed to prove the theorem and build a graph which is about that same size, not much larger. It will be maybe polynomially larger, but not really much more. If this graph has a three coloring, I conclude that statement has a proof of length L. If this graph does not have a three coloring, that does not. So this is a new language for giving proofs. Instead of trying to prove to you that this theorem is true, I can just say, look, take the graph that would come out of this reduction. Here is the three coloring for it. Okay. You might say, why is this helpful? Well, here is the reason it's very helpful. It's very easy. If you are the referee for this paper, it's very easy to prove the error. You say, look, there was supposed to be an edge between this particular node over here and that one here, but both are colored red. So you took, this is the coloring of all the vertices that you're giving me. If two of these nodes, which are both red colored, have an edge between them, and I prove to you that your proof is wrong. So it's very local way of proving that something is erroneous, that a claimed proof is erroneous. Classical proofs did not necessarily have this feature. It was not possible to go locally into one spot and say, here's the error. You might have had to go through all kinds of, computations. It depends on the verifier that you use. If you use the graph coloring verifier, then it says, oh, look, just look at these two places. So this tells us that, this game of what kind of a format should a proof be written in, and I'm saying write the proofs as graph coloring proofs. This can be very useful in some steps of sort of checking the correctness of a proof. Okay. So I hope that made some sense. So the error is very local. There are just two improperly colored regions, and that proves the thing. So just as a quick aside, so is P equal to NP or not? This is sort of a famed open question by now. So there's lots of consequences. If P equals NP, then pretty much all the current basis of cryptography is gone. We can set up an alternate framework for it, but it would be very delicate and much more fragile than this. So we wouldn't. But on the other hand, all optimization problems become easy. You just have to wish for something and it'll come true. That's P equals NP. Okay, you just express a statement in terms of what would a solution look like, and a solution will be found. So that's P equal to NP. It's just too much to hope for. If P is not equal to NP, this is consistent with current thinking. So it's baked into almost all the theory that exists. So it's not like you will radically alter everything, but it would be very educational. This might be the first way in which we will be able to prove, build sound crypto systems. Almost all cryptography built today is based on assumptions which may or may not be valid. And these assumptions are just mathematical ones, leave alone physical ones, like does the, can we build a quantum computer, etc., which would jeopardize even more of this space. So that's the general things. And there's a school of thought which is also exploring the question, is this independent of Peano's axioms? I'm not enough of a logician to comment really about, how strong this possibility might be. There's a popular science book by Devlin. So the P versus NP question is one of the Clay 6 famous problems in mathematics, each one associated with $1 million prize. And when this list of problems was published, Keith Devlin said, of all the Clay problems, this is the one that might be the one to find the smallest, simplest solution, the shortest solution, and even by an amateur mathematician. Okay, so clearly, that's one opinion. And likely, why do you think this might be the case? Well, you think, if I have to give you an algorithm for 3 coloring, maybe it's an algorithm which is a page long, and some analysis, which will be something simple also, and then I have the algorithm. So if you believe P is not equal to NP, I don't think you would assert that this could be a small, it doesn't, an amateur mathematician is not going to understand the question of how do you even express P is not equal to NP. It's much easier to express the answer P equals NP. So this is probably what Devlin was thinking about. On the other hand, there's this colleague of mine, Lance Fortner, who runs a blog, and he says, well, if somebody shows P equal to NP, then they can prove any theorem they want. This is really, you just say, look, I've just proved P equal to NP. I have this algorithm which can solve all NP-complete problems. Theorem proving is an NP-complete problem. I'll prove all the theorems I want. There are 6 theorems out there, each worth $1 million. I'll cash in on all of those. So you take away all 6 million, not just the thing. This is very sound reasoning. Okay, the one above, I'd be less trusting of. So in some senses, P equal to NP is sort of the mathematics complete question. You can do all of mathematics if you could prove P equal to NP. So we expect the answer is no, but that's not a proof. All right, so turning to more recent history, up until now, we've sort of we've come up with a notion of what does it mean to be a proof. And this notion is essentially a computational notion. If you don't have a notion of finding a proof is hard, checking a proof, verifying a proof is easy. And if you don't have a notion of easy and hard, you can't have a notion of proofs versus theorems. Okay? Just stating the theorem and the length of the proof should not be a proof. And that's the thing that we've come up to. But in recent years, what computer scientists have started doing, this is like 1980s onwards, is started injecting randomness into this process. And you might say, why would you want to inject randomness into something which is as pristine and pure as logic? Computer scientists have realized over the years that somehow randomness is just an essential ingredient that we have that is very helpful, but also sometimes completely necessary for certain forms of interactions. So it's helpful in the sense that there are many problems out there that we know where randomized algorithms are much faster than any deterministic ones. So these involve computers tossing coins in order to determine what to do next. And since we'll tell it exactly what is the distribution from which you're sampling, so typically just toss a coin, which is unbiased, heads or tails. And if it's heads, do this. If it's tails, do that. So these kinds of things, should be still considered very, well-defined processes. It's just that it maybe allows you to explore different parts of the search spaces. So it can potentially speed up algorithm, but it's also necessary, as Nash proved, for equilibrium behavior. There are many games for which there's a mixed equilibrium, but there's no pure Nash equilibrium. It's needed for coordination in a distributed environment. It's needed for cryptography. If I don't pick my private keys, my passwords with some randomness, my mother will be able to guess what my passwords are. So somebody will be able to guess what you are doing if you're being deterministic. So the only basis of cryptography can be built on randomness. So it's it's a fundamental resource in the theory of computing. So it was natural that we would ask, what can you do with logic? And this brilliant work by Gulwasa-Mekali and Rakoff, and also by Babai, considered the following setting. So far, the notion of proofs has been something written. You write something, send it to a journal, and the journal sends it to a verifier who verifies the proof and comes back with an answer. What about an interactive process? Okay, most of our conversations when you're teaching something to students are interactive. Can these be somehow different? And in here, maybe you are the verifier, you're trying to check some, I'm claiming some statement is true, you're asking me some questions. You might toss a coin saying, look, if the coin comes up heads, I'll ask about this part of the proof. If it's tails, I'll ask about that part of the proof. I write down two lemmas saying A implies B, B implies C, and the theorem is A implies C. Well, you can toss a coin and decide which half of these you want to verify. Maybe. So there are many options that are available when you are doing things interactively. If you're going to predictably always go into a certain direction, if you're not going to be random, then I can possibly, it doesn't really, I can just anticipate all your questions and just say, when we start this thing, you will ask me this question, I'll tell you this as the answer, and then you'll ask me that, and then I'll give you that. If you decide to be random, I can't say, oh, you might ask this question or that, and then this one or that, and then that one or that. So suddenly, as the length of the interaction grows, the tree branches out exponentially. And so there's exponentially many things that I have to be prepared for in order to prove something to you. And this can potentially be much more beneficial. So initially, these folks proposed the model, gave some very intriguing examples of problems that we knew to prove interactively, and then came a very compelling theorem which is completely nailed it down. So striking examples, there is the Pepsi versus Coke test, it's a blind taste test. You can actually simulate a version of it in a purely mathematical setup where I say, oh, I have some graph in hand, and I want to know if it's isomorphic to this other graph. And I sort of hide the graph behind me, permute the vertices and bring one out. And you have to tell me whether it was the left graph or the right graph. If you can tell me, then these are not isomorphic. And if you can't tell, then they're probably isomorphic, right? So, it's a proof of graph non-isomorphism. It's a proof that Pepsi is not have the same molecules as Coke. So these are very basic things you can actually do, and these are really beautiful things that you can do with interactive proofs. We don't know how to do classically. Here's a couple of other statements that I really like. In particular, this one. So imagine I come up to you and I say, oh, here's a theorem, and I want you to prove, and the statement is there's a proof of length L. And you're a very diligent student. You go off, you run your 2 to the L time algorithm, and you explore the whole search space, and you found no proof works. Now, how are you going to come back and convince me? I don't have 2 to the L time. I have L time. I have L square time, if you want even. Prove to me that this statement has no short proof. There is no classical way we have of writing the statement down. Interactively, actually, you can prove it. Okay, I won't tell you how. You don't see how. But at least the statement should be very clear. Look, how do you prove that a statement does not have a short proof? Seems very hard to do that short of enumerating all the possibilities, but there is a way. And it's completely non-trivial. It's not something that you would think of, off the top of your head. It took many years of work before somebody discovered this thing, and it's a part of this famous result called IP equal to P space due to Shamir and Lunford-Nokalov and Isan. So it comes out of this theory. Yeah.
So what do you mean by short proof?
Good. I specify a length L, and I say, prove to me there are no proofs of length L. But I will only give you polynomial in L time of interaction. Okay. So I'll ask you questions which may be L bits long, your answers may be L bits long, etc., etc. We can actually, in sort of L square time, I can actually, you can convince me of this fact. Okay. So L is a parameter, L is considered short, 2 to the L is considered long, L square is also short. Okay. Great. So this is, and there are even more sort of stunning results in the space. There are these things called zero knowledge protocols where I can convince you of any statement I want while giving you no additional information other than just the fact that the statement is true. Okay, so somehow there's a sort of a very nice notion which is actually useful in cryptography, where you might want to say, I am allowed to make this transaction, but that should not give you anybody who's sniffing on the transaction and listening to it the ability to simulate the same transaction again tomorrow. I withdrew $100 from the bank. It doesn't mean you get carte blanche to withdraw $100 whenever you want. So in cryptography, you really care for this thing, and you can actually build beautiful mathematical definitions and achieve them. And these are all possible because of this randomness and interaction in proofs. So my work in this area came up with this, started with this kind of a question. Do proofs have to be read in their entirety to be able to verify? Okay, so this is something that we've been looking at before. Notice that when the graph 3 coloring thing that I said, when I wanted to verify the proof, I had to go through the entire graph and make sure every edge was colored. In order to convince you that there is an error in the proof, I only needed to point to 2 things. Now I don't want to actually read the whole graph and read the whole coloring. I just want to do something like pick a random edge and say, oh, look, it's not colored right. Will this work? And almost the entire history is of, logic is sort of thinks no. The answer is, proofs have to be read in entirety. Here are a couple of examples of proofs that I found. Clearly, based on the bottom line, something must be wrong, but, you have to read this entire proof carefully to find out where is the one sentence that is actually wrong. Okay. I don't know. I think the more you can find on this thing. So over here, I think there's a divide by 0 error. And over here, there is, you take, this is the positive square root and that's the negative square root. And you're just saying they're both equal. Okay. So anyway, so you can Google for more such proofs and find lots of them. The interesting part about these proofs is it's not every line is wrong. It's not, how do you what do you do with this proof and sample? How do I sample it randomly to discover an error? Okay. It cannot be done for this format of a proof. The PCP theory says for the conventional format, you have to read the whole proof. But we know from the theory of NP-completeness that the format is up to us to choose. And if we choose a more careful format, maybe you can get something much more sort of powerful. Okay. So any verifier, as long as it's running in polynomial time, is good. And we just want to say, look, if you have a standard proof of length L, then the new proof should not be much longer. I mean, saying the new proof is going to be of length 2 to the L, but I'll verify it very quickly is no good, because writing this new proof is almost as hard as verifying the old proof by yourself. You could have enumerated everything. You really want it to be a short proof, almost as short as what you started with. And if the theorem has no proofs, then you should not accept anything. Okay, if this is not a true statement, you should not be able to accept it. Any such system is what we call a PCP system, a probabilistically checkable proof system. And okay, now we would say you should not accept any proof, but you're doing things randomly, and somebody might just even write a random string. If you're reading randomly 100 bits of the proof, somebody writes 100 random bits. If there was any way you could accept it, then there's a 2 to the minus 100 probability that you would accept this random string, because it's 100 bits and there's some binary sequence that you would accept. So you should allow these kinds of proof systems to have some error, which says, look, depending on how many bits I read, I'm maybe getting more and more confident in the proof, but it's not a function of what you wrote, what the theorem is, and so on. It's just a question of how I toss the random coins. And if I toss more coins and they're all genuine, unbiased, independent random coins, I will get more and more and more confident in the proof. That's the notion of a PCP verifier. We were able to prove in 92 that there is such a format in which the verifier only reads a constant number of bits in the proof. The constant is independent of the theorem, the proof methodology that you're using, et cetera, nothing depends on, it's a universal constant. And yeah, okay, the thing may be, okay, the probability with which we may be rejecting things may be much smaller than a half, maybe like 0.001. Yeah.
Would there be occasions where you want to verify randomness?
Would there be? Absolutely, yes. I mean, in all of these things, we would like to say that the randomness is being completely trusted, but there definitely are natural settings where you might want to ask the question, can I verify randomness? And I'll probably talk about that a little bit later in the talk. So for instance, somebody is running an auction on eBay, and every time when you bid high, somehow, the random allocation says, oh, you get this thing and I'll take your money. And every time you bid sort of competitively low, somebody who's bid a slightly lower price still gets the thing, because, oh, that's because there's randomness in the system. I would definitely like to explore eBay's randomness when auctions and always losing them, or somebody says, look, if I owe you, the lottery is going to be decided tomorrow, but it's a random thing, but you always lose. I mean, so why is it that, friends and relatives of things, people who are just outside the, excluded zone are always winning the lottery? Now, give me the proof that this is actually genuinely random. It makes a lot of sense. It's not quite fitting the scope over here so far, but actually people have applied this kind of a interactive verification methodology to think also about verifying randomness. Great. Maybe I'll try to jump ahead to that. So let's see how are we doing on time. I don't think I have so much time. So I had some analogies trying to explain where do these PCPs come from. I won't tell you about it. The whole idea is combinatorics was the wrong. Combinatorics and logic are the wrong space to be building proofs on. Algebra is the right space, and this is algebra, very simple, algebras in your undergraduate textbooks and so on. These are what actually help us build really solid things. We have to do new things with them, which are connecting algebra to randomness, but so on. There are some things in these slides that you might be able to see. I think this is actually correct, but this is the whole reduction that sort of is the essence of converting graph coloring into an algebraic problem. And once you have this, proofs become much, much more robust and verifiable. And that's what we do. Okay. So by now, by the way, these proofs are like just become the technology is sharpened really, really, really nicely. You have an original proof of length L. How much longer does it have to be in order for it to be verified probabilistically? We started with L to the million, so still a polynomial, so it's okay. But by now it has been brought down to L to the 1.000001. Anything 1 plus epsilon for any epsilon of your choice. Even better is possible. And what about how many bits do you have to read? 3 bits of the proof, real bits. If the proof is valid, you will accept it probability 1. If it is not valid, if the theorem is false, and you should accept no proof, then with 50% probability, you will reject it. So all of these are really remarkable numbers. If you don't like 50% probability, roughly the scaling is for every additional bit that you read, you can reduce the probability of error by another factor of 2. It's just completely everything that we know that you could want is all achieved here. Okay, so this is like, this theory is completely like ready to, there's no numbers which are sort of holding them down. And lots of very nice math plays a role in this thing. Why did we care about this concept of a PCP? Not so much because we were interested in logic and randomness, not interested because of cryptography either. It was really the following thing. We understand that theorem proving is like combinatorial optimization. In combinatorial optimization, say the traveling salesperson problem, there is a related problem which says, I don't want the optimal tour, but just give me a tour which is not more than 10% more expensive than the optimum tour. It's a very reasonable question to ask. I'm not an ultra optimizer. I will settle for a moderately good solution, but at least not ridiculously bad. Just give me anything which is within 10% of the best. we never knew how to say this was going to be a hard problem for any choice. Now, 10%, 1%, 0.00001%, we didn't know how to say this. When you look at this sort of, there is theorem proving TSP, approximate TSP. What is the question that you want here that would allow you to bridge, say that this problem is hard? PCPs. If you can say that having a, so in the PCP setting, I can say, find me a proof that the verifier will accept with 90% probability. Well, if it's going to accept a 90% probability, the only reason it does is because the theorem is true. So a proof that is accepted with 90% probability is the same convincing power as the proof which is accepted with 100% probability. If the theorem was not true, you would have accepted any proof with probability at most 50%. So approximation is built into this translation, and now you can transfer it over to through the CARP world of reductions to all the problems in the world, and almost all of them are shown to be hard to be approximate by this methodology. So anyway, there's a lot of stuff in the text here, which I'll skip. In the current directions, there were two things I was going to mention. One was some new variant of the PCP conjecture, but I will sort of skip it. Instead, let me talk to you very briefly about just proofs and quantumness. And this is also related, some senses, to randomness. So imagine you have, by the way, my knowledge of quantum computing is kind of very, very shaky and weak. But I've tried to say some things which are not false, but on the other hand, I don't know the full history and the context over here. So if I'm not giving you all the right credits, my apologies for that. So there is this game called the CHSH game. In our world, it's expressed in the following way. There is a verifier who's talking to two entities, Alice and Bob, and sends each one a bit, X and Y. And they should both respond with 2 bits, A and B. And you will accept if the logical AND of X and Y, which is going to be another bit, equals the XOR of A and B. Okay, so XOR is the sum modulo 2. And somehow, multiplication and addition just don't mix in any universe, and in this universe also they don't. So if you try a classical strategy, the simplest thing that you can do is always Alice responds with 0, Bob responds with 0. A and B are both 0, their XOR is always 0. And if either X or Y turned out to be 0, then you win the game. If not, you don't. So it's a strategy which, if X and Y are uniform and independent bits in this example. So in this universe, you win 3/4 of the time, but you lose, the game rejects you 1/4 of the time. Now, it turns out, if Alice and Bob have some shared entanglement, there is a strategy which allows them to win with probability 0.85 in this game. Okay. So why is this interesting? This is a proof that Alice and Bob have shared entanglement. Okay. This can be used to prove that they have shared entanglement. If they have many entangled bits and they claim we have many entangled bits and they want to prove it to you, you run this game. If 85% of the time they're winning, then this is a proof that they are sharing entanglement. This, for some skeptics, this could even be considered a proof that quantum, the axioms of quantum physics are actually true, are measurable, are verifiable. So this is very interesting. It's an interactive proof with 2 provers, Alice and Bob, and they're proving to you that some quantumness exists. There are analogous methodologies which say, well, we can also prove randomness to you, but I don't quite understand those statements, so I want to talk about that. In modern extensions, people have extended this thing in remarkable ways. In particular, 2 things. Results that I am aware of is Urmila Mahadev has this beautiful result which says that any quantum computation where we are saying, look, here's some quantum computation, it is doing something where I cannot check the answer. It is necessarily in polynomial time. It's not an NP. Quantum computation is not necessarily sitting in NP, so it's not something where I can say, oh, I did the calculation, the output is correct. But you can prove any of that by an interactive proof, again, by methodologies similar to interactive proofs. Another beautiful result is basically due to this collection of authors, G, Natarajan, Vedic, Wright, and Yuan, which shows the base. I mean, it's still in the sort of review stages, so most likely it'll turn out to be that by now all the creases have been ironed out, but it's definitely, there are lots of brilliant ideas here. Maybe not everything will work out, but really plenty of good stuff here. They are giving an interactive verification of all computable functions. Well, okay, this is using two provers who share entanglement. You can turn all of these interactive protocols in their head and just think of it as, what is it doing for us? It's some way of proving to you that we have shared entanglement. If two people want to prove they have shared entanglement, these are ways in which you can do it. The problem with all of the results, I mean, anything built directly on CHSH is, I can prove to you that I have entangled particles with Arthur, or Arthur and I can prove this to you. But in the process of proving things to you, we've just lost all the entanglement. Now we can't do anything else with it. So we can prove it, but then it's useless. Can you do anything beyond? Can we somehow only use half of the bits that we have to prove things to you and use the other half? This would have been considered a remarkable result 20 years ago. What we have from this result of G, Natarajan, Vedic, Wright, and Yuan is, it's not half the bits. You can take a completely, really negligible number of bits. So in order to prove that Alice and Bob, in order to prove that they have n entangled particles, they can, for instance, lose log n bits, and you take any number of logs. I put as many as I could on this page. Any number of these things, you use up those, eat up that much, and you convince the others that you have n bits of interaction, of entanglement. It is remarkable, this result. It's really beautiful and important. All right, so that's where we are. The future, maybe I'll very quickly say one thing. So PCPs, in particular, these probabilistically checkable proofs, as a method to understand inapproximabilities, the traveling salesman problem, hard to approximate or easy to approximate, can satisfiability, blah, can three coloring be done something differently? All of these questions were amazingly good success in terms of addressing it, changed the landscape over there completely. But as a positive method, I mean, it is an efficient way of proving things. Up until now, almost nobody ever used this to do anything positive with it. It was just a negative concept. I will prove to you all these problems are even harder than you thought they were. Now, finally, we are seeing something, but it's in some space where, we don't know whether the space is important or not, but these applications seem to be right on target. They are giving very good ways of verifying large amount of blockchain computations, and maybe this process could actually make them more sustainable. Why is this so rare? Because we really, the notion that a proof is somehow written down and give you the whole thing is almost never really happens. So the general assumption in proofs is there is some small collection of axioms, and then you have some small theorem, maybe medium-sized theorem, and then the proof is kind of very large. And if this is the case, then we would be very happy to use PCPs to say, oh, let's not save you from reading all of this. But what actually happens in reality is that mathematical proofs assume a huge amount of context. And they build proofs based on this context. So there is this book by Lehman, Layton, and Meyer. It's the MIT course notes for their introductory discrete mathematics course. And it says, by some estimates, a proof that 2 + 2 = 4 in ZFC would require about 20,000 steps. Okay, so, and they say, so we will use a huge set of axioms to shorten our proofs. We are now in a universe where the number of axioms is just huge. The theorem is moderate, and the proof is, actually smaller. In this setting, PCPs are not the right concept to be looking at. So one of the things that I'm very interested in is sort of the communication of proofs. How are we actually communicating proofs between humans, and what kinds of assumptions and context assumptions can we make about the reader and the writer of the proofs, in order to be able to say that verification will usually be successful. I don't know how many of you have sent papers to some journals, and the one referee comes back saying the proofs are completely incomprehensible. The other one says the proofs are totally elegant. It happens, and this happens because there is this mismatch of context between the writer and reader, and something that's, I think, very much worth exploring. So I think that's all I wanted to say. So that's it. Thank you.
Well, thank you very much for an insightful, provocative, and stimulating talk.
Thank you very much.
I think there will be a great deal of discussion against. Are there questions here in the room? Ms. Katak.
So, thanks for the nice talk. And so I have a question. Why is it possible to verify encoding intangible by already consuming a very low level and sample theory? Any intuition or
So, so this is the question is about how did this result that I mentioned about the quantum verification of entanglement? How is it even possible? How are you able to reduce it? It's not easy to explain what is going on, but it's building on the machinery of interactive proofs and converting a lot into the quantum universe. And one of the things that in the past we've already seen that there are proofs of length, and that you can verify by reading a constant number of bits in the proof. But the randomness that was being used in order to do this verification was logarithmic. So something that's happening in the quantum world, which I don't completely understand, is you can almost set up the hypothetical next level question saying, if I had log n bits of randomness, how would I verify your proof, and tell me what I would read? And somehow you can ask the next layer of questions and pose it as a new quantum interaction challenge. And you've gained an advantage by going from a statement of length n to a statement of length log n. And if you look at all the things that have happened in this thing, nothing has actually, no interaction has actually happened. So, and this is what is being exploited in the quantum scenario.
I mean, I'm just wondering whether there isn't a way of sort of using Bell's inequalities with, basically any infinitesimal entanglement to sort of prove whether in physics that's not somehow equivalent to what you're saying.
My guess is that this is the first sort of proof, formal analysis along those lines. That, I mean, the Bell's inequalities is what gave us the CHSH game, for instance. I think, yeah, and it may even be just a expression of what was confirmed in Bell's inequality in my language. That's all maybe that is changing. But in order to go beyond that, I think, I mean, somehow that was a setting where we could confirm that there's some amount of entanglement, but in the process of confirming, we would have lost it.
And also verify uncoded entanglement using a very tiny number of qubits. Is this some kind of quantum version of PCP?
Yes, it's a quantum version of an interactive proof. And in fact, the paper is about what do interactive proofs, what power do they have when the provers have shared entanglement? But it's not a quantum version of PCPs, which is a similar but different question. There is a quantum PCP conjecture, which is open, and I don't know what's its outcome.
Do you mind stating that?
So roughly what the quantum NP-complete problem that we are aware of is something you're given a local Hamiltonian and you'd like to estimate its ground energy state. And somehow I think the NP-complete problem is saying, well, distinguishing whether the ground energy is 0 or positive, but positive may be only exponentially small, is what is the current. So you have to detect energy levels which are like 2 to the minus n, and that is the NP-hard problem right now. The quantum PCP conjecture would like to say that, well, constant energy state is indistinguishable from 0 energy state. And I think there are people out there who believe this statement could be, yeah, it could be as hard as the original, but we don't know how to prove it.
So there's a concept in quantum information called magic. Have you thought about that?
No, actually, I've been very curious about the concept of magic and trying to understand what it means computationally. But I would be very curious to hear about a quantum version of it. Question in the back?
I have a question on whether this mechanism will be adopted in some general review system. For example, in my undergrad thesis, I did over 30-page proofs to Klember's secretary problem, which is only 2 pages long. So basically, the second examiner said that it's very hard to do the proof. That's the problem we made, and so basically, that's my question. What's the
Right. So let me sort of set aside one myth, which is that proofs are used to verify the correctness of theorems. It's nearly not true in humanity, and it's not true in mathematics either. Okay, what we use proofs for mostly is to convey some ideas. So the whole goal the game we are playing with proofs in reality in mathematical journals is very different than what you've been told it's supposed to be doing. We try to give, and this is sort of emerging in this thing, the proofs are always never written completely formally. There are always some high-level ideas of needs to be done, that needs to be done, and the rest of it will work together. Yes, of course. So at the end, you could hope for a completely mathematically verifiable proof, but these are certainly very long. And even just doing automated verification is just too hard for this thing.
Thanks.
Are there questions from people online?
Yes, I have a question. I hope you can hear me well.
Yes,
So
very well.
yeah, the question is about the setup. So you have two parties. I'm somewhat familiar with the protocols, Arthur and Mervyn. So they are entangled. So the interaction happens with another third party?
Yes, correct. So in these quantum setups, these are following previous work on what is called multi-proof or interactive proofs. So the Alice and Bob is what I call them. Arthur and Merlin is a phrase that is often used when Merlin is trying to prove something to Arthur.
Okay.
But now we are considering a setting where there are 3 players at least. I call them Alice, Bob, and V for verifier.
Okay.
And the verifier wants to check something, and only Arthur and Alice and Bob have shared entanglement.
So who answers from Alice and Bob? Both of them answer to the verifier, or one of them? How does that work?
Good. Okay, sorry. More about the setup. Alice and Bob are set off in some light years away so that they can't communicate with each other. And questions are addressed specifically to one of them. So I will ask one question of Alice, one question of Bob, another one of Alice, another of Bob, etc. And we try to set it up somehow so that the two of them could not really communicate with each other, except by going through me.
Yeah, thank you for the answer. But the next question is that the whole setup is about propositional logic. So how much of these results generalize to first order or higher order logics?
The way we think of these theorems and proofs, I mean, the mathematical language of theorems and proofs is not really around propositional calculus. You can create instances of the same problems in propositional logic. But at the end, we really are talking about anything that you write down as a sequence of, I mean, at the end, the only thing that we care is you give me a verifier, and the verifier will be able to read a theorem and a proof and confirm that the proof is a proof of the theorem. If you have any mechanism, any form of logic for which there is a verifier, it is captured by this methodology.
Okay. Yeah. My motivation was that the completeness and soundness, they're all different for different orders of logic. So how much?
Right. So the way we think of it, you give me the verifier, and then I will build all kinds of other equivalent verifiers who will preserve the set of true statements and false statements. But you could have 3 different verifiers for whom the set of statements that are provable are different, and for each one we can set up a PCP variation, etc.
Okay, yeah, the existence of a verifier, yeah, that takes care of these some premises. Okay, thank you.
Sure thing.
Good question, Raj. Okay.
So, so in the proof of article of PCP, people use the locally testable code to construct the PCP, right? So do you think it's possible, like, to consider quantum low degree polynomial testing? And
So what I understand is, yes, the quantum MIP result does have some quantum variation of a low degree testing problem, but that problem is somewhat cleaner in that all the elements that we're talking about there, the communication channels are all classical. It's only that the communicating parties have shared entanglement. I think the quantum PCP and the locally testable codes versions of the quantum locally testable codes questions are all hovering about, our codes in quantum space, or qubit-based codes. And these, here we don't know if these locally testable ingredients would exist. And if they existed, we don't know that the quantum PCP statement conjecture would follow. So this is there. I mean, it's a possibility. This is what people, I think, are exploring and why people are exploring it. But I don't know how much progress there is or what they currently believe.
oh yeah, for example, if we assume the locally testable quantum locally testable code exists, kind of prove in the classical. In the construction of classical PCP move to the quantum case?
Not that I'm aware of. I think people who worked in this area, I mean, I'm just relaying statements that I've heard from others and I don't completely understand, but they don't know why the NLTS conjecture, which was resolved recently, might have anything to say about quantum LTCs. And they don't know if quantum LTCs will allow them to get to quantum PCPs. But since this was the path in the past for classical objects, maybe this is a path we'll try now.
Thank you.
Sure.
Are there any other questions? Any other questions online? So I'd like to thank Madhu again for a wonderful talk.
Thank you for all the questions. Pleasure to be here.
We're going to skip 1 week. We'll be back in 2 weeks.